Welcome back. So the previous lecture we have seen one of the most fundamental theorems in terms of how to show stability of dynamical systems. The definition of stability is quite complicated in terms of these epsilons and deltas, and we have seen the Lyapunov function method. If we can find some function that satisfies a couple of conditions, then we can prove Lyapunov stability. And of course, if further conditions are satisfied, we can show asymptotic and eventually exponential stability if we can, right? In this lecture, we will pretty much go through a bunch of examples, mostly handwritten type of things. So if you actually consider this second order ODE, this in reality represents some kind of pendulum with some damping. We want to show whether check if this particular system is stable or not. Whatever the notion you may eventually show, whether it's Lyapunov or asymptotic or whatnot, we'll see, right? Now, one of the most difficult things about Lyapunov function, though it is the only method that legitimately claims to have a result on stability, is actually finding this Lyapunov function candidate or Lyapunov function eventually, right? So it ends up being quite a trial and error type of method. But on the other hand, if we are dealing with some mechanical system or physical system, then typically energy function works, right? Because if you have a system, typically energy dissipates, so energy, the initial energy will always go lower than what it started with, and then that in a way satisfies our Lyapunov function stability condition, right? If you remember, basically one of them has to be positive definite, that typically energies are, and then the second thing is the rate of change of energy has to be negative, strictly or soft, it doesn't matter. So again, that's like assuming there is enough dissipation of energy in nature, and then eventually the system is going to remain bounded to start with, and if there is sufficient dissipation, then basically it will reach a point where it's not going to move from there. That is the equilibrium. So in order to apply this Lyapunov function theorem, one needs to, technically speaking, we need to first change this into state space, and I'm going to, as usual, define theta 1 as theta and theta 2 as theta dot. When we do that, we can do this theta 1 dot is equal to theta 2 as the first equation, and theta 2 dot is equal to minus theta dot, which is minus theta 2, minus g over L sine of theta, which is theta 1, right? So these are the two state space equations, and first things first, let's check the equilibrium points. You can see that theta 2 has to be 0. The right hand side of both the equations have to be 0. So all the equilibrium points will satisfy this condition theta 2 equals 0. Once theta 2 is equal to 0, we will also get sine of theta 1 is equal to 0. So basically all the equilibrium points are the form 0, 0, pi comma 0 in radians, 2 pi comma 0, and so on and so forth, right? One can restrict your differential equation just to this, 0 to 2 pi without including 2 pi, and then that way we'll get only 2 equilibrium points, but that's the bare minimum we get, right? So we are going to focus on this one single equilibrium point and then basically check for its stability, right? So when we actually do this kind of mathematics or calculations, one need not really worry about transforming everything into state variables. Of course, fairly obvious that theta and theta dot are the two variables we have, so we write the function directly in terms of those things and move forward, right? So is v greater than 0 for all theta dot not 0? What does it mean for theta dot not 0? It simply means one of them is non-zero, right? Both of them don't have to be non-zero, but one of them have to be non-zero. So if you actually go and see this particular expression, if theta dot is 0 and theta is non-zero, then the second part is going to be positive, the first part is going to be 0. But the third part, 1 minus cosine theta, is going to be always non-negative. So there certainly for theta non-zero, you'll immediately get V is positive. Similarly, for theta dot non-zero, right, the first part is going to be positive, the second part is going to be non-negative, and the last part is going to be 0 if theta is equal to 0, right? So no matter what, we can clearly see that for either one of them non-zero, we'll get positivity. So that means V is LFC. Okay. So the only other condition that we have to look for is basically compute this V of theta comma theta dot and see if that in somehow is strictly less than 0 or less than equal to 0. So when we do that, we'll get theta dot theta double dot plus theta dot times theta dot plus theta double dot, and 2g by L, you know, sine of cosine of theta, the derivative is minus sine of theta, so we'll get something like theta dot sine of theta, and the sine, original sine, will get cancelled, right? So remember, theta double dot, well, let me first simplify. So we'll get theta double dot plus theta dot plus theta double dot and plus theta dot whole square plus theta dot theta double dot plus this 2g over L theta dot sine theta. Okay, remember theta double dot is minus theta dot minus g over L sine theta, right? Let's remember that, and then we can continue. So wherever theta double dot is there, we can substitute it. I'm going to kind of take this and this combined together. We'll get 2 theta dot plus theta times minus theta dot minus g over L sine theta. Of course, the remaining terms is theta dot plus theta dot square plus 2g over L theta dot sine theta. Okay, so by substituting, so we'll get something like minus 2 theta dot square minus 2g over L theta dot sine theta, which will cancel with the last term there, minus theta dot minus theta times g over L sine of theta plus theta dot plus theta dot square plus 2g over L sine theta dot. So we will be able to cancel this and this and this and this, and this and this will simplify to minus theta dot square. So eventually we get minus theta dot square minus g over L theta sine theta. Okay, so this is what we have, V dot of theta comma theta dot, right? Now what can we say about this? Clearly less than or equal to 0. So immediately 0 is Lyapunov's table. What else can we say? Well, in fact, if you pay attention, when theta is 0, this theta dot is say non-zero, let's say. So then minus theta dot here is going to be strictly negative. When theta dot is 0, theta times sine theta can be 0 if we are far off from 0, but close to theta, theta times sine theta is always positive. I mean, that's a result that we have known. So basically minus of g by L over times theta sine theta is going to be negative. So in other words, this further implies 0 is asymptotically stable. Okay. And so we shown that v dot is less than or equal to 0, but we actually showed further that basically v dot is indeed strictly less than 0 for all non-zero theta dot. And what about exponential stability? Unfortunately, this v is not straightforward. Of course, one can think of this 1 minus cosine theta. If you recall, cosine theta itself is 1 minus theta square and so on and so forth. We'll get something like theta square there, right? And in which case, at least locally, one can show that it satisfies the typical quadratic condition we have. Okay, and eventually when we get here, v dot is theta times theta locally, right? And then it's going to be strictly less than 0, but it also satisfies the condition that we have in terms of v dot less than or equal to minus epsilon v. So in reality, it takes much more work, because we just cannot use just these blindly approximations and then hope that things will work, but we have to put the rigor. Eventually one can show, okay, 0 is also exponentially stable with some work. Okay, so that's the way one has to go about. One of the things we forgot to check is basically if v of 0 is comma 0 is 0, and then that's trivially satisfied. This part is 0, this part is going to be 0 at 0, this part is going to be 0, so that all the conditions of Lyapunov function theorem are satisfied to show first Lyapunov stability, then asymptotic stability. We didn't show the details of exponential stability, but that's the details are left to you as a homework, right? So we'll go on to the next example, and the next example is again, it's a nonlinear example. We have this state space equations x1 dot and x2 dot, and this v of x1 comma x2, and clearly v of x 0 comma 0 is 0, and then v of x is positive for all x non-zero. I mean, how do we check that? Basically take x2 is 0, and then this gives positive number. If x1 is 0, this gives positive number, and if both of them are non-zero, then we get positive anyway, right? So that's the way to check positive definiteness. Once we have that, then the only thing we have to do is the compute v or dot, which is in this particular case x1 dot plus x2 cube times x2 dot, right? So that we have to use the equations we have, x1 times minus x1 plus x2 cube plus x2 cube times minus x1 minus x2. When we simplify, we will get minus x1 square plus x1 x2 cube minus x1 x2 cube minus x2 power 4, right? And you can see that this and this cancels, and that will give us minus x1 square minus x2 power 4, which of course is strictly less than or equal to strictly less than 0 for all x1 x2 non-zero. Okay, so we therefore conclude that 0 is Lyapunov stable and of course asymptotically stable, right? I mean, technically we should just say 0 is asymptotically stable, and then that implies Lyapunov stability, but we understand what we mean by that. What about exponential stability? Unfortunately, because of the fourth power, we cannot show, the higher powers cannot be lower bounded by quadratic expression, so we cannot show exponential stability the way the theorem that we have. Perhaps it's still exponentially stable, for using some other method, but not using the method. So we don't know if this is exponentially stable, and most probably it's not, right? This one, if it had the coefficients that look there, if half and 1/4 or something like that, then we could write something like v dot is less than minus epsilon v, and then we could actually show in that particular case v is going to be exponentially decreasing with time, and then that says something about each one of these things decreasing at exponential decay. But even that we don't have. We can indeed show, this is less than or equal to minus x1 square minus half x2 power 4, which is equal to half minus half v, okay, sorry, minus 2 times v. Yeah. So what we were saying is basically, this has the form the components of x1 square and x2 power 4. By just realizing that, one can show that this is indeed less than minus 2 times v. So we will get a conclusion that this implies v of t is going to be less than or equal to v of 0 e raised to minus 2t, okay, or something like that. Now, so that is quite useful. I mean, we may not be able to show technically the exponential stability the way we defined it, but showing that the Lyapunov function in this particular case is quite a nice simple function, quadratics and quartics, that is going exponentially down to 0, and that's good enough to know. I mean, then that also shows something about rate of convergence, right? So it's not just simply asymptotic stable, it is much more than that, okay? Let's move on to the next example. So here we are taking this up as a challenge and see what happens if we try to guess the Lyapunov function candidate, right? So perhaps we can try something like a x1 square plus b x2 square. This is almost the first thing that one can try, right? And I mean, one of the simple things. So if you pick this thing, one of the simple thing is basically v of 0 is automatically 0, and then v of x is going to be positive for all non-zero, right? So that's kind of free. So therefore we can compute v dot, which is basically 2a x1 x1 dot plus 2b x2 dot. And when you substitute in all this, we'll get 2a x1 x2 minus 2bk x2 sine x1, right? I mean, one can see locally, by picking a equals b k, right? We will get, let's say, I don't know, this entire thing is equal to 1 or something, k or something like that. We will get 2k times x1 x2 minus x2 sine x1, right? I mean, if you are doing approximate mathematics, basically sine of x1 is close to 0 is x1, and then therefore we get this less than equal to, is exactly equal to 0, and then showing Lyapunov stability. But that's not the way we can do, because when we approximate it, we don't know what's going to happen to the higher order terms, and then that higher order terms, if they make it positive, then this entire thing is going to not work out, okay? Those of you who understands this better, of course, the Taylor series expansion gives you x minus x cube, and then it will actually give you a positive term, and that's scary, okay? So anyway, that's something to think about. Just because we found some function where v dot may be positive, what does it mean, and things like that. We will postpone that. For one function, if we find it positive, does it mean this system is not stable, and things like that. In fact, we'll contradict ourselves in a second and say, basically, we can try all kinds of typically one can try even more general quadratic function. That's something like that. I'm going to put it. So x1 plus x2 square plus b x2 square. One can even imagine a times x1 square plus b of x1 x1 plus x2 square, and you will convince yourself there's nothing more general than this, right? That is guaranteed to be a positive definite function. You can find a more general quadratic function, but that need not be positive, right? So then what is the and then you will see that even for this more general function we'll end up with basically difficulty in terms of showing v dot negative. So it's not easy, right? So perhaps we can try, because of the fact sign there, perhaps we can try something like 1 minus cosine of x1, right? And then when we take v dot, we will get 2a x2 dot minus, actually plus b x1 dot sine of x1, right? So that's going to give me 2a times x2 dot is minus k sine of x1, so x2 sine of x1, and x1 dot is x2 plus b x2 sine of x1. So by letting b equals to a, some positive number, right, we will get v dot is equal to 0. So this shows 0 is Lyapunov stable. Okay, so what will happen if we want to show asymptotic stability? Clearly, this particular Lyapunov function cannot show that this particular system is asymptotically stable. Does not mean that this particular system is not asymptotically stable. It's just that we are unable to show the theorem of Lyapunov or asymptotic stability, or for that matter exponential stability. We can only show Lyapunov stability, right? So the lesson that we learn from this example is basically, sometimes the standard quadratic functions may not work, so we have to go creative. But how do we know that something like this will work? Well, only experience gives you such guesses, but beyond that there is really not much hope in terms of finding a general method for Lyapunov functions. We will look at some specific methods at a later point in terms of how to construct Lyapunov functions, but in general it's quite difficult. So here is another example, and I'm going to basically straight away pick the standard ax1 square plus bx2 square, right? So therefore this is LFC, Lyapunov function candidate, and therefore we can directly jump to computing v dot. I'm going to get 2a x1 x2 dot, sorry, x1 dot plus 2b x2 dot. When I substitute that, 2a times 2a x1 times x2 minus x1 times this x1 square plus x2 square plus 2b x2 times minus x1 minus x2 times that function, right? So when we write this, 2a x1 x2 minus 2a x1 square plus x2 square plus 2b, sorry, minus 2b x1 x2 minus 2b x2 square times x1 square plus x2 square. So I'm going to pick now a equals b equals 1. Okay. Why do I want to pick? Because these cross terms x1 and x2 products are always going to be a problem in terms of showing non-negativity. Not always, but sometimes it's easier to set them to 0. So I'm going to pick a and b equals 1, so that that part they cancel with each other, and resulting, basically after manipulating, you will get minus 2 times x1 square plus x2 square times x1 square plus x2 square. Okay. This is indeed minus 2v square. Okay. We'll come back to that in a second. So what we have is v dot is equal to minus 2v square, so which is essentially strictly less than 0 for all x non-zero. Okay, so the zero solution is indeed asymptotically stable, and of course that implies more simply a Lyapunov stable. Okay, now the fact that v dot is equal to minus 2v square, can we conclude anything more than that? Well, certainly we will not be able to show something like asymptotic stability exponential stability for one reason. When you actually manipulate this, we'll get something like dv by v square minus is equal to 2 dt. So that implies log of vt over v0 is equal to 2t. Okay, so we use this v dot is equal to minus 2v square, and we can rewrite that in terms of differentials, and that will give us basically, when we integrate it, 1 over v 0 to t is equal to 2t, and that implies 1 over vt minus 1 over v0 is equal to 2t, and so we can eventually conclude that this is going to be equal to 1 over 2t plus 1 over v0, right? And this is clearly, the v is certainly not decreasing exponentially, and that was brought to show any exponentials, right? So we'll go to a similar example next, and it's much more interesting in some sense. So we will consider again x1 square, put a half or not, it doesn't matter, half x1 square plus x2 square, and then start computing v dot, right? So the trick most of the time is going to be simply pick some quadratic function or some function that is easy to show that it is positive definite, and that will satisfy the first condition. The second condition will simply be computing v dot. So when I do that, so I'm going to get x1 times x1 dot, and I'm going to jump ahead and do this. And instead of x1 dot, I'm going to directly write that x1 dot expression plus x2 times x1 plus x2 times x1 square plus x2 square minus 1, which I'm going to get, you can clearly see the first one will give you x1 times x1 is x1 square, then the second term is going to be minus x1 times x2, which will get cancelled with this cross term here, and then eventually I'll end up something like x1 square plus x2 square times x1 square plus x2 square minus 1. Okay. It turns out this is going to be equal to v times v minus 1. So if you are in a region v less than 1, then v times v minus 1 is going to be negative, strictly negative. Right? So clearly, v of 0 is 0. So at 0, v is less than 1 anyway. Okay. So that means around the origin you have a region. In fact, for all x1, x2 such that x1 square plus x2 square less than 1, we have v dot is strictly less than 0 for x1, x2, not equal to 0. So therefore, we conclude that this system is asymptotically stable. The zero solution is asymptotically stable. Okay. But we have this v dot is equal to v times v minus 1. Sorry, actually this is 2 Yeah, I should have picked b to be x1 square minus x1 square, and then let's modify that. Yeah. So when we get this, we can actually solve this and then see that v is not really exponentially decreasing, but in fact we have a finite escape time, and simulations show that indeed the systems go off to infinity in a finite amount of time. So we have exponential, we have asymptotic stability. Sorry, I'll get back and then talk about that in detail, but not exponential stability for the time being, right? But not exponential stability. So let's draw a picture and then see what happens. Suppose 2v equals 1 corresponds to a circle, right? Now inside this circle, we see that everywhere we'll have this kind of behavior, and one can show wherever we start, we will end up with equilibrium point. Right? But if you start outside, this v dot is going to be positive, so v dot is going to keep on increasing. So that means wherever if I start outside, I'm going to go on. Right? If I start within this thing, basically, then we will have a nice convergence to the equilibrium, which is what is very required for asymptotic stability, but not exponential stability. Right? So what I was saying is basically outside one can show that this is going to have a finite escape time. This is going to go off to infinity. So in fact, at some point one must try running some of these examples through MATLAB and then see indeed the behavior that we see here is also observed in numerical simulations. But remember, numerical simulations can simulate up to one or two initial conditions, and therefore we cannot really say much more than that. Right? But nevertheless, it gives us a comfort zone that the theory and numerical simulations are consistent with one another. So perhaps we will look at some MATLAB examples at a later point of time, but essentially Lyapunov method is indeed an analytical method. Thank you.